Okay, before we dive into the meat of the webinar, I'm going to present our amazing speakers that we're having today. We starting with Evelyn. Evelyn is a PhD candidate at the University of Alberta, and she works in the Department of Chemical and Materials Engineering. And her group focuses on gas separation processes with focus on carbon capture and direct air capture. We also have with us Harsha Nistala, also a PhD candidate at the University of Alberta, who is also part of the group on the Department of Chemical and Materials Engineering at the University of Alberta, focusing on gas separation processes, especially focused on carbon capture and direct air capture. And we also have with us Malte Glaser, who is a PhD candidate in the Department of Chemical and Petroleum Engineer at the University of Calgary. His work focuses on the techno-economic and life cycle assessment of direct air capture processes. So we're very excited to have all three of these researchers here. And a note to the audience, if you have any questions throughout the presentations, please feel free to drop them in the Q&A tab that is at the top level of your screen. The chat is disabled, but we will get to those questions at the beginning of the session. So please feel free to drop them at any moment. And then without further ado, I'll pass it over to Evelyn.
Thank you, Luisa, for your kind introduction. Hello, everyone. My name is Harsha. And let me start by giving you and setting a context for direct air capture. So in 2025 alone, 39 gigatons of carbon dioxide was released into the atmosphere due to human activities. And this led to an atmospheric CO2 concentration of 432 ppm, which is the highest ever. Due to the adverse effects of high CO2 concentration on climate change, global warming, and adverse weather events, there is an urgent need to reduce CO2 emissions and try and limit global warming to less than 2 degrees Celsius. The Intergovernmental Panel on Climate Change, or IPCC, modeled various emission pathways to try and regulate global warming and reduce CO2 emissions. One such pathway is shown here. The key takeaways from this is the key drivers for reducing CO2 emissions in this pathway are rapid decarbonization of industrial sectors, widespread electrification, and conventional carbon capture approaches. However, you would appreciate that it is not possible to decarbonize all sectors, particularly distributed sectors like aviation or agriculture. And this is where carbon dioxide removal or CDR technologies play a key role. These technologies are aimed at capturing carbon dioxide from the atmosphere. And for this reason, they are also sometimes referred to as negative emissions technologies. So CDR technologies are expected to offset emissions from hard to abate sectors like aviation, agriculture, and also partially to account for any temporary increase in the CO2 emissions above the emissions limit required to limit the global warming potential. And IPCC notes that all analyzed pathways use CDR to some extent. Now, CDR is based on three core principles. One, the CO2 or carbon dioxide needs to be captured from the atmosphere. Two, the captured CO2 needs to be stored durably. And three, both capture and storage have to result from deliberate human intervention. Therefore, CDR is an umbrella term for a suite of technologies, some of which include bioenergy with carbon capture and storage, direct air capture and storage or DACs, enhanced weathering, biochar, and afforestation or reforestation. It is said that CDR technologies have a global deployment could have a global deployment of 5 to 15 gigatons of CO2 per year by the year 2050. There is also and these would result in a cumulative removal of CO2 of 150 to 1180 gigatons by the year 2100. And in this particular webinar, we will focus on direct air capture and storage, or DACs. So DACs is the method of removing CO2 from ambient air by any chemical or physical process and enriching it to a high concentration, let's say more than 95%, and then subsequently storing the captured CO2 underground in geological formations. So the process of capturing and enriching CO2 is the DAC part of the process, while transporting and storing the captured CO2 is the storage part of the process. And as you can appreciate, given the very low concentration of CO2 in air, which is 400 ppm or 0.04%, we are literally cherry picking CO2 molecules, 400 molecules from a million molecules. And that is one of the biggest challenges that we will talk about in this presentation. And as I mentioned, the CO2 needs to be concentrated to greater than 95%, which means we are increasing the concentration by about 2,400 times, a very significant increase. Now, there are many different processes for direct air capture, but all of them can broadly be classified into three main categories based on the kind of material that is used to do carbon capture. The first category is liquid-based or absorption-based capture, where liquid chemicals such as amines, amino acid salts, or alkali solutions are used to capture carbon dioxide. The second category is solid-based direct air capture, in which solid materials are used to capture carbon dioxide. These are further classified into processes like adsorption, membranes, processes that use membranes, or processes that use other minerals. And lastly, the third category of DAC processes involves phase change, wherein the materials change from one phase to another, for example, freezing of liquids or melting of solids. And in this webinar, our focus would be on adsorption-based processes, which we will talk about a little bit more going further. Now, as we talked about just a slide ago, the key challenge of DAC is having to concentrate from a very low concentration of 400 ppm to a very high concentration. And this, as you would appreciate, involves filtering more than 2,400 kilograms of air just to capture 1 kilogram of carbon dioxide. And this comes at a significant energy penalty. Practically, we know that direct air capture processes involve energies anywhere in the range 6 to 12 or even more megajoules per kilogram of CO2. Just to give you context, this is roughly 10% of the energy that can be generated by burning 1 US gallon of gasoline. And DAC is particularly hard. It is technically challenging and expensive, but it becomes particularly hard when it needs to be operated at very large scales that it is required. Some of these challenges have been acknowledged by DAC companies like Climeworks. Climeworks is a Switzerland-based DAC startup and is one of the first few DAC companies in the world. 2 years ago, they wrote an article on their website talking about the reality of deploying direct air capture in the field. And they have been, Climeworks has an installed capacity of about 40,000 tons of direct air capture per year. While the challenges persist, there are many different startups that are actively working in this area and trying to make DAC work. And some of these numbers point to that. For example, up to 2023, 11% of all CDR startups are based on DAC. Parallelly, 29% of all CDR startup funding went to direct air capture projects. Now that we have understood the challenges that DAC faces and some of the realities that companies are seeing in the real world, let's look at the fundamentals that actually make DAC work. So as I said, in the subsequent part of the seminar, we will be talking about adsorption-based processes for DAC, which use a special solid material known as a sorbent. So in this photograph here, we show you Luvitit, which is one of the commonly studied sorbents for DAC. Macroscopically, it looks like spherical particles of the size 0.5 to 1 mm. But if we zoom into one of the particles and look at the surface of the sorbent, it has chemical chains which have an affinity for carbon dioxide. That is, CO2 or carbon dioxide is preferentially stuck to the surface of these chains when it is exposed. As you very well know, air along with carbon dioxide also has significant amount of humidity or water vapor. And these sorbents also have an affinity for water vapor. So when these sorbents are exposed to air, in addition to CO2, water also sticks to these materials. We particularly know that for materials like gluvatate, water cooperates with CO2, that is, in the presence of water, more amount of CO2 is attached to the surface of the sorbent. Lastly, one of the key properties that actually enables DAC to work is the behavior of the sorbent when the temperature is increased. We know that for a material like gluvatate, when the temperature is increased, the amount of CO2 that is there on the sorbent decreases, or CO2 is released from the sorbent, and this allows us to design a DAC process and make it work. So to make a DAC process work, particles of the sorbent are packed in a vessel such as this in a random fashion. So the particles are packed randomly with no particular structure, and the voids in between the particles, as you can imagine, it's not perfectly packed. There are empty spaces between the particles. These are known as voids. And when air is passed through the vessel containing the sorbent, the CO2 and the water which are present in air stick to the surface of the sorbent, while the nitrogen and the oxygen present in air will fill up the gaps or the voids in between the particles. This is the first step known as adsorption. In the second step, which is known as evacuating and heating, the airflow is stopped, and the other end of the bed, we apply vacuum. This is applied to remove the nitrogen and the oxygen which are present in the empty spaces, and this is necessary to improve the purity of the final product. The vessel may also be heated externally to prepare it for the next step of the process. The next step is called desorption. And in this step, as the temperature of the bed increases, the CO2 and the water present on the sorbent will start to come out. Steam may also be used sometimes to accelerate the release of carbon dioxide, that is, to get carbon dioxide out more quickly. And as you can imagine, the CO2 and coming out from this step is hot and humid. So it is cooled down, it is compressed to remove water, then it can be transported and sequestered at a storage site. Now, the bed at the end of the third step or desorption step is very hot. So it needs to be cooled down. And most often, air is used to cool down the bed again. And when it cools down, it comes back to its original condition where it is ready to absorb more CO2. So these sequence of steps 1, 2, and 3 are repeated in a form of a cycle to continuously capture CO2 and release it and store it. Now that we have seen how a DAC process can work, we ask ourselves the question, what other information do we need to know in order to deploy DAC at a very large scale? So at the scale of the sorbent, we need to understand how the sorbent behaves under different circumstances. For example, under different temperature conditions or under different humid conditions. We need to know how much CO2 and water can it hold, let's say at minus 20 degrees Celsius versus plus 40 degrees Celsius. We also would need to know the rate at which CO2 will go in and come out of the sorbent. And we also would want to know, does the sorbent degrade? If yes, what is the lifetime of the sorbent? All the information that is gathered at the sorbent scale is crucial for designing a DAC process. So at the design stage, we try and answer questions like, what is the minimum amount of energy and sorbent required to make the DAC process work? Does the shape of the sorbent matter? And so on and so forth. And this design information will then be useful for making deployment level decisions. For example, um, we would like to know answers to questions like, what is the impact of varying weather conditions on the DAC process? Or where is the best possible location to construct a DAC plant? And as you will appreciate, we are going from information gathered at the millimeter scale on the sorbent to a meter scale at the process level to technically kilometers scale at the level of deployment. Now, you may ask, do we know answers to all of these questions? Our response would be not really. So we know answers to some of these questions, but there are gaps that we do not know of. And we feel that it is important for us to fill these gaps to hopefully gather answers so that they can be used for policy level decision making. Therefore, in the next part of this webinar, my co-speakers and I will discuss these gaps and talk about how we are trying to address some of these through our work, starting with measurement.
Hi, everyone. My name is Evelyn, and today I will be focusing on measurement techniques for DAC that have been developed at the University of Alberta in Dr. Rajendran's lab to date. Sorry, I think there might be a slight lag. Okay. So experimental data in literature for direct air capture materials and processes is limited, which is why we have developed this infrastructure in the lab to fill these knowledge gaps. However, experiments are very time consuming, so predictive models are necessary to reduce this experimental load, but to build these predictive models, accurate data is needed for both input information and for model validation. This figure represents the current DAC availability and difficulty to obtain said data for materials in direct air capture. So this figure can be broken down into two main groups. The material characterization data, which when I talk about equilibrium, I'm talking about the amount of carbon dioxide or water that can absorb or stick to the material. And when I speak about kinetics, I'm talking about how fast the carbon dioxide or the water can absorb to the material. And the data available in literature is mainly for unary carbon dioxide and water for various materials, but the kinetic data is much more limited in comparison to the equilibrium data. And even more importantly, the binary carbon dioxide water data is quite scarce. And as in air, water is always present and at various relative humidities. With the carbon dioxide we're trying to capture, we need to understand how that basically affects the carbon dioxide kinetics and equilibrium data and vice versa. And then as well, process characterization data such as quantitative data for process model validation, as well as process key performance indicators or KPIs are also limited in literature. Okay, so for material characterization, we use an experimental technique called dynamic column breakthrough. How this technique works is if you have a column which is filled with a material of interest, you're then able to basically look at the different concentrations of CO2. And how you do this is you first fill the column with a flow of nitrogen, the yellow part that you can see in the column, as it does not stick to the material. And for adsorption, we make a step change in inlet concentration that you can see here, and we flow that into the column. And then this is the blue part. And that carbon dioxide will flow through the column and stick to the material until it reaches equilibrium. And then for desorption, we make a step change in the opposite direction. So from CO2 back to nitrogen, and then the CO2 is pushed off the material as the nitrogen flows through the bed. And what we can get from this experiment is breakthrough curves. And these breakthrough curves we can get from a concentration detector, and they give us two key pieces of information. They can give us the area behind the curve in this gray, gives us the equilibrium loadings, or the amount that has adsorbed onto the material. And then the shape of the breakthrough gives us an idea of the kinetics, or how fast the CO2 is adsorbing. And then, so for this project, a microscale dynamic column breakthrough system was built to measure both the unary and binary carbon dioxide and water equilibrium loadings, as well as kinetics. And its operation range is between 1 and 2,000 ppm of CO2 and a relative humidity between 0 and 95% at temperatures between 10 to 90 degrees C. This instrument was co-funded by NRCan and Total Energies, and I would like to give a special thanks to Jim Sawada for facilitating this instrument being built. So these breakthrough curves are an example of what this instrument can do. So this is on luteite, a material that Harsha mentioned previously. And these experiments are conducted at 400 ppm CO2 at various relative humidities and at 30 degrees C. The yellow breakthrough curve is at 0% relative humidity, whereas on the far right, the dark red is at 95% humidity. And you may remember that I mentioned that the area behind the curve tells you how much CO2 has adsorbed onto the material, which means that at higher RHs, there is more area behind the curve, which means there is more loading and more CO2 adsorbed onto the material. And so what you can do is you can do some math and you can get an actual value for how much CO2 was loaded instead of just qualitatively speaking about kind of if some is more than others type things. So this is a unary isotherm or isotherms, and I'd like to thank Bhupesh, a previous colleague who worked with us for collecting these on luteite. And what you can see is that you have an amount of CO2 versus a concentration at different temperatures. So as Harsha mentioned, at low temperatures, you have more CO2 capacity. And then when we get up to like 100 degrees, we have less CO2 capacity. But this is a unary CO2 isotherm. And if we want to take those breakthrough curves, as we mentioned earlier, and look at the actual CO2 loading or the values of it, we can see that at 0% RH, we had about a 0.75 millimole per gram loading, and at 95%, we're all the way up to 1.5. So you can see the impact of water with that changing relative humidity. We almost doubled our CO2 capacity. So it is quite a significant change. And then we also have another instrument, and this is called the DAC Process Demonstration Unit. And its purpose is to provide model inputs and model validation, and to determine key performance indicators for DAC, such as purity, recovery, and energy requirement. And when I say purity, it's how pure the CO2 is from the process. Can it reach pipeline specifications? Recovery is how much CO2 can be recovered from the material in comparison to how much CO2 we had to flow through the bed or column. And then energy requirement is simply how much energy is needed for the process. And then what we can do is with the predictive process models, we can understand the trade-offs between these three or more key process indicators to try to optimize our process cycles. And again, I'd like to thank our sponsors, Enercan and Total Energies, and Jim Sawada again for facilitating this instrument being built. And so the current process being studied is shown to the right. It's similar to the process Harsha mentioned previously. The adsorption step is where CO2 is being adsorbed from the air onto our material. And then in step 2, we use external heat to prevent steam condensation and the difficulties it adds to measurements. And then a steam desorption step occurs where steam is put into the column and carbon dioxide is removed from the material. In the future, humid cycles as well as processes that avoid external heating will be studied. Okay, so when running an experiment, we measure 3 main types of information. We measure flow, which is on the top, temperature, which is in the middle of the graph, and then composition, which is on the bottom. And what you can see first is this is the adsorption step. And in the adsorption step, if you look at the bottom figure, you can see the breakthrough of the 400 ppm of carbon dioxide from our concentration detector. And then in the middle figure, you can see the temperature spike of the heat released from that carbon dioxide bonding on the material. And then if we go to the external heating step, the main thing that I'll get you to focus on for this one is that in the middle figure, you can see that the material is heating up to 105 degrees C. That's all that's really happening here. And then in the desorption step, things get a little bit more complicated. So if we look at the bottom part of the figure, you can see that carbon dioxide is concentrating as the steam is absorbing onto the material. And then eventually the rest of the CO2 comes out with steam, which is part of the reason why we need to basically take the steam and condense it out, because we need to get dry CO2 at the very end for storage. And then in the middle, you can see the temperature, and you can see the increase in temperature from the steam absorbing onto the material. And then both the top figure, which is the outlet flow, and the bottom figure together can be used to calculate the total amount of CO2 removed from the material, can be used to calculate KPIs such as purity and recovery, and to see how much steam actually absorbs onto the material. And then all of this is information that can be then used to design DAC systems, which my colleague Harsha will be discussing. Thank you.
Thank you, Evelyn. So in this part of in the design stage, as Evelyn mentioned, the information that is gathered from the measurement stage, such as the capacities and the rates, are used to design DAC processes. Particularly in this study, we try to estimate the energy and the sorbent required for a DAC process, and to answer the question whether the shape of the sorbent matters to DAC. So as I was mentioning previously, all DAC plants have an air handling problem. Due to the very low concentration of CO2 in air, a large quantity of air, roughly 2,400 kilograms of air, needs to be filtered to get just 1 kilogram of CO2. This is roughly the amount of air present in a small 5-story building. And the most common way in which this is done is to place the sorbent particles randomly in a bed. As we discussed earlier, this is what is referred to as a packed bed. But as you can see, the flow of air in a packed bed is not straight. It is curved because of all the obstructions of the particles, and therefore it requires more effort and energy to move the air through a packed bed. Therefore, a new kind of a DAC vessel known as a monolith has been proposed. So this monolith has parallel sections that go from one end to the other end. And if you look at the cross section of the monolith, it has an inert support or walls, and the sorbent is painted on the walls like paint on a wall. And due to the straight channels that are present in the monolith, it is much easier for air to pass through the bed. By the way, monoliths are not new. You would find monoliths in the catalytic converters of your cars. So when it comes to the effort and energy required to pass or move air through the bed, the monoliths have a win. But when it comes to the amount of sorbent present in the vessel, packed beds have high amount of sorbent because of the way they are packed. In a monolith, since it's just a coating of the sorbent on the wall. So the obvious question then for us is, does DAC work equally well in both kinds of vessels? To answer this question, we could have done experiments, but we went in a slightly different direction. We developed a computer model of a DAC process. So think of it as a flight simulator that can take properties related to the sorbent. It can also take different process parameters, for example, the flow rate of air, the temperature conditions, the flow rate of steam, and so on and so forth, and then run virtual experiments. So this computer model can run virtual experiments rather quickly. So we ran about 5,000 virtual experiments in each of the DAC vessels. This is equivalent to roughly 5 years of operation at different conditions in each of the vessels. And running all these virtual experiments can then tell us what is the best possible process performance, and what is the minimum amount of energy required to get that, and what is the least amount of sorbent required to achieve that best performance. So let's look at some of the results from this study. So the results are shown in the form of an XY plot, where the x-axis tells us the sorbent required to produce 1 ton per day of carbon dioxide from air. The amount is given in tons of sorbent. And the y-axis shows the amount of energy required to actually make that DAC process work. So this is given in terms of 12 megajoule per kilogram of CO2. Just as a reminder, 12 megajoule is roughly 10% of the energy that would be generated by burning one US gallon of gasoline. So for the packed bed, we see that the sorbent requirement is anywhere between 10 and 50 tons, with energy ranging between 10 and 14 megajoules per kilogram. And this amount of sorbent is roughly the amount of sorbent that will fit into 1 to 5 trucks of the size that are shown here. And as you would appreciate, we would want to move to the lower quadrant of this graph, where the amount of sorbent required is low as well as the energy requirement is low. So let's see where the monolith or the monolith kind of vessel falls on this graph. So we see when we go from a packed bed to a monolith, the amount of solvent required reduced significantly, but the energy requirement also went up significantly by about 60%. And the reason for this is the inactive walls that are present in the monolith. These walls do not have any capacity to capture CO2, so they just behave as an inert, and this requires them, and the DAC process requires that we heat them to take the CO2 out. So there is an energy penalty of using monoliths which have inert walls. So then we ask the question, what happens if we remove the wall and just deal with a monolith that has just the sorbent without the walls? And we see then that the energy requirement falls back to the level of that of a packed bed, and the sorbent requirement also falls significantly compared to a packed bed. So this study tells us several key things. First, we were able to estimate the least amount of energy and the sorbent required for two kinds of DAC vessels. We found out that the shape of the sorbent can also impact the energy and sorbent requirement, and therefore the shape can be a key factor in DAC design, and we suggest that it should be considered when designing DAC processes. With that, I hand it over to Malte for the next part of the seminar.
All right. Hello. I'm Malta. And I guess so far we've pretty much talked about the the lab work that we're doing and the very detailed modeling. And I want us all to take a step back and look at the big picture. What's the deployment of direct air capture going to be? And in this case, we always wonder how and where are we supposed to operate and build direct air capture? And the reason we're asking ourselves this question is essentially threefold. And the first is that direct air capture is a rather expensive technology. What does expensive mean? In oversimplified terms, it means that it is significantly cheaper to just build a solar panel, for example, on your roof than having a direct air capture system in your garden. And in other words, we want to make sure that once we actually spend all the money, we're using this money most in the most efficient way. But it's not always about the money. It's also about what kind of technology do we even want to buy. And we talked about this already at the beginning of this webinar, that there are different materials, for example, that we could use. There are different structures that we can use, right? And there are also, if you want to call it, like different chemical philosophies of direct air capture, right? And we can imagine that given that this planet is very big, that different types of direct air capture perform differently across the globe, and we want to make sure that once we pick this location, we're also using the proper direct air capture system. Speaking of location, it also matters that we should build, like once we invested the money, once we have the money available, we want to make sure that we build the DAC system in the proper place. What does that mean? Again, in oversimplified terms, we probably shouldn't burn down a forest just so that we can then build a direct air capture system, right? They're national parks. Maybe we should protect them. So the location and where are we building and operating direct air capture is an important consideration. And this is essentially what we're trying to do next. And we started with the province of Alberta in Canada, which in itself is humongous. Me as a European, I always think about this, that Alberta is several times the size of most European countries. So you can imagine that once we go from north to south or from east to west, the conditions which direct air capture is exposed to will change quite drastically, and therefore will also influence the performance of the technology. So what we decided to do is we said, let's go through every single coordinate in this province and determine what is the performance of DAC and where should we build the next system. However, talking to family and friends, they always ask me, what are you going to do with all the CO2 that you've captured? And we are saying, okay, let's also look at potential storage sites. So where could we store the CO2 that was previously captured by the DAC system? And this is shown here in kind of the green shaded areas. And then, as I said previously, we also want to make sure that we're not building the next DAC system in Jasper or Banff National Park. So in general, we should probably consider other environmentally sensitive areas. And what we then decided to do is we put all this together into some kind of optimization decision-making framework to kind of inform on that decision where and how are we supposed to build that. Once this is done for Alberta and Canada, the next idea is to extend this analysis to all the other provinces in the country, potentially even the territories up north, and then if we have time and computational resources further down in the States and maybe the entire North American continent. All right, so that in a nutshell explains why we're here and like what motivates our work. And to answer all these questions, we needed a toolbox, and we call this toolbox a smart direct air capture. And in its core, it has a DAC model. We talked about our modeling approach previously already, and effectively that is like, as we called it, the flight simulator, right? Like we want to understand how does direct air capture perform once we expose it to different conditions, say in northern Alberta compared to southern Alberta. However, direct air capture is a technology that needs a lot of electricity, and we need to make sure that that electricity is available. Again, there are different approaches to this, and we took a rather simplified approach where we said, let's just connect DAC to the electricity grid. Effectively, that means that every single electron that we're using is that comes with the associated electricity cost and upstream emissions. What does that mean? We need to pay for the electricity, and regarding the upstream emissions, that electricity has somehow been generated. We may have used a solar farm, a wind farm, or maybe we burned natural gas. And all this has its own emissions that we send back into the atmosphere. So we need to consider this in our decision making, right? What's next? So direct air capture, the air kind of gives it away already. It needs air. It processes air, and air changes as well. The conditions of the ambient air change. We have temperature, we have relative humidity, and all these things change, and they also impact performance. So we said, let's also consider ambient conditions, and as I said, temperature, humidity, and also the pressure, like air pressure. And let's have those kind of change every single hour, similar to the conditions of the electricity grid. And what we now have is a model that has like hourly changing inputs, and what we get is any kind of variable in our system now becomes a function of time. In other words, at any given point in time, we know what is the temperature in our system, what is the pressure in our system, how much CO2 have we captured or adsorbed at any given point in time, how much CO2 are we desorbing. So we have all the information available, and we can use this now to determine like certain key performance indicators, KPIs. And we decided to go for something that a lot of humans care about. It's always the money, like how much money are we actually spending and how much CO2 do we capture? So what's the dollar per ton of CO2 that we've removed or captured? And we call this net carbon capture cost. We put all this into an optimization framework, and part of an optimization is always certain decision variables that we can change to kind of influence that net carbon capture cost. What does that mean? We can change how long are we adsorbing for? How long are we desorbing for? How much air are we processing? What's the temperature in the system? And like all these things can be changed to improve, and you may even want to say optimize the net carbon capture costs. It's always difficult to optimize such a system because it's not really linear, and therefore we can't really reach a global optimum, but we can at least improve the performance and be confident enough that the solution that we found is, well, not bad or near optimal. I guess it depends on how you want to phrase this. Anyway, long story short, we have this framework, Smart Direct Air Capture, and we can now apply it to the entire province of Alberta to see where should we build the next system based on the things that we want to consider, as I said, cost and like storage sites and those kind of things. And we did this, again, kind of coming back to that first question, like how and where. And this framework helps us to answer the where question here. And we see the map of Alberta color-coded, and the green areas refer to more suitable sites, and suitable means, as I said, like from a cost perspective in relation to national parks or other environmentally sensible areas and storage sites. And then more yellowish areas refer to places that probably aren't the best places for the next direct air capture system. And what we see here is that the net carbon capture costs vary quite significantly across the province. And we also see that like the availability of storage or kind of the existence of national parks further influence our decision making. So that kind of is a take on the where box. And the how box is significantly more complicated to cover, and we most certainly don't have enough time to cover this in this kind of introduction into direct air capture webinar. So that would be something for the future. And quite frankly, that's not the only thing that's left, because there are many unknowns or kind of next steps for direct air capture research. And quite importantly is the uncertainty when it comes to data measurements, right? So we talked about this at the beginning, that we need to measure, like how does the material perform once we expose it to direct, like put it into the direct air capture system? And what's the influence of water? Like what's the co-adsorption of water and CO2? What happens if we run and use the material for like days, months, years, like how much does it degrade? There are so many unknowns that we would need to understand. We need to put this kind of knowledge into the models and need sensitivity analysis to understand the influence of the assumptions that we're using as of right now. Once we've done this, as I said, the next step would be to kind of put everything back into the model and expand that model. What does it mean? So far, we've looked at Alberta as a province, but Canada is big. There are other provinces. The entire world is big. So we want to expand that scope. And I also briefly talked about this link between the direct air capture system and the energy system. So where's the electricity coming from? And as of right now, we're assuming that it's just kind of drawn from the grid. But maybe the direct air capture system will influence the conditions of the grid, and we should consider this. Or on the flip side, kind of the grid influences how direct air capture should operate. So this kind of interplay between these major systems needs to be understood and properly modeled. Once all this is done, we're coming back to the money, because that's ultimately what people care about. Like someone needs to pay for direct air capture. And we don't really, we want to understand how much is it going to cost us to remove a single ton of CO2. And again, there are a lot of assumptions that we've kind of used as of right now to get somewhere, but it's important, like how much does the sorbent cost? Speaking of degradation again, like how often do we need to replace the sorbent? And if we do so, how much is that going to cost us? How much is it even going to cost us to build the DAC system in the first place? So all this, as part of the techno-economic assessment, becomes important to inform kind of the general public on the potential of direct air capture. And lastly, speaking of potential of DAC, ultimately we're doing this to remove CO2 from the air, right? But we also need to consider, are we actually removing CO2 or are we just capturing it and then further up the chain, kind of upstream, we've already emitted all this CO2. In other words, if we burn a lot of fossil fuels just so that we can build and operate direct air capture, maybe it doesn't even make sense because we are not really removing CO2. So that's a whole kind of life cycle assessment question that also needs answering. And there are a lot of unknowns because we don't necessarily know how, like what is the climate impact of the solvents, for example. So these are kind of the big four things that still need kind of investigation. But we're pretty confident that we can get to some stages there at least, and then combine everything into a major framework that allows us to answer some system level and kind of policy relevant questions that we summarized in a very easy and straightforward way, where we're saying how much direct air capture can a country like Canada do, and how much will it cost us? But yeah, so that's pretty much it for now. We do want to acknowledge that there's more out there. You can read if you're interested. This is just like a snapshot of papers. There's hundreds of DAC papers out there, all of which are interesting to read. So go for that one. And we wouldn't be here today without the funding from, well, pretty much the government of Canada, as well as in-kind support from Total Energies, Corning, and Mitax. And most importantly, we need to acknowledge our supervisors, Sean and Arvind, for their help, without whom we definitely couldn't have done all the work we've already done. And if I'm not mistaken, we do have a couple of minutes left for some Q&A sessions.
Yes. Thank you guys for that presentation. That was excellent. How can we make the record capture more efficient and where here in Canada? Because we're short on time, the questions that we do not get to answer here, we will do our best to answer and get back to you. You can also reach out to the contacts on the screen if you have any further questions that we don't get to cover here. So just as a big reminder, because you talk about the humidity cycles, how they need to be studied and how they impact the capacity of the sorbent. What is the reason for more carbon dioxide absorption due to the relative humidity?
Hi, I can take that question. Okay, so we're still, I'll say, in the process of figuring this out. My best guess or feeling is that there have been some papers published about how amine density does play an important part. And with unary CO2, two amines are needed to basically bond to one CO2 molecule. But when you have water present, it is possible for a reaction to occur where it's just one amine can hold on to the CO2 and then the other side of the CO2 is bonded to the water, if that makes sense. So you're able to increase your capacity potentially because of that. But there is another kind of field, I'll say, or a group of individuals who think that in materials like this, it's because of swelling. So it actually kind of opens up the amine bundle in the presence of water, which is able to make it easier for the CO2 to bond. So it's still kind of unknown, but we're working towards hopefully figuring that out.
Thank you. It is really great to see all the amazing research that is going on and what's coming. This question is actually for you, Malte. Is the comparison between solar panels and direct air capture valid since they don't provide the same service? One is avoidance and the other removal, avoidance versus removal.
It's funny that you would ask that because we literally had the same conversation when we were kind of putting the slides up. And no, they don't achieve the same thing, of course. But the reason we still wanted to kind of mention this is that people have seen solar panels. People have maybe their neighbor, maybe themselves, they have solar panels on their roof and they have a feeling for how much that may or may not cost. And few people have seen, and even less people have an idea of how much direct air capture is going to cost. So I was just trying to kind of point out that a solar panel on your roof is expensive, but direct air capture in your garden would be significantly more expensive, even though they, technically speaking, achieve different things. And I just saw that you had a second question, so I'm going to go for that one as well. How do we model the annual variation in performance? So the model that we have has is a dynamic model, so it can go and kind of use every single hour as an input. And yes, we go through all 8,760 hours in a year to calculate how does the performance vary for every single cycle, for every single day, every single hour, and yeah, pretty much the entire year. And we could go through several years as well if we wanted to.
Thank you. Okay, and then what is the lifetime of the most optimal absorbent? Is this something considering to be studied further?
I could take that one as well. I wouldn't say there is an optimal material because different materials will behave differently in different places in the world. But obviously, the best or the best lifetime would be forever, because a lot of these amine materials, especially for DAC, do degrade. So unless you have a process solution that can deal with that degradation, the lifetime is something you need to consider. But as there's no optimum material, we wouldn't know a lifetime for it specifically.
Fair enough. And then one last question before we have to close the webinar, but a reminder that you can reach out to the contacts on the screen or let us know to the CanCO website if you have any further questions. So leukotite is not stable under oxygen atmosphere. How do you handle it?
Yeah, so when we're studying the material to basically get information for our models, we keep it in an environment where that isn't an issue. So all of our experiments are kept in nitrogen, so we don't actually introduce oxygen into the problem at all. But in terms of its long-term stability, it obviously does degrade at high temperatures in the presence of oxygen. So it's more how are we going to design our cycle in a way that we can hopefully mitigate that from happening. And I'm not saying that Leukotite is the end-all be-all adsorbent. If there's a better amine material that comes along or another material in general that is more stable, that would probably honestly be a better option. We're just studying this one because it's been reported a lot in literature and we needed to get somewhere and it's commercially available.
Okay, thank you for that clarification. And actually, maybe we have one time for the last question now. It might be a bit broad, so keep it brief. But like, Huda is asking, how easy is to scale direct air capture up?
I mean, I can say a couple of words there. I guess you could argue that there are arguments that it is that you can scale it. There are arguments that kind of say the opposite. We're in the early stages of direct air capture technologies. There's a lot of research going on right now, as we've kind of hinted at during the webinar. There are very few real-world examples, so I don't necessarily know that we're in a position to kind of give a very kind of fundamental, like reasonable answer. As I said, people are talking about the modular design of direct air capture and that you could easily scale it, but on the flip side, there's also not really evidence that in the real world that this is being done. So I'd be careful putting like a definite statement out there as of right now, at least.
Yeah, fair enough, fair enough. We're all asking ourselves that question as well. And so this was a great example of the great work that is going on at the University of Alberta, Calgary, and all the universities involved in the CanCO project. We are going to have a more in-depth mini-series of webinars, of videos further along throughout the year. So please stay tuned. Visit our website, the CanCOinitiative.ca, and I will, with that, thank you guys for that great presentation, the audience for the amazing questions, and I'm going to unceremoniously finish the webinar. Have a great day, everybody.